Hey, I'm Max. I'm going to be walking through the Spring 2023 final exam for Calc 2, just to hopefully show how all the problems are done and the general approach to solving certain problems, giving certain inputs real quickly. I have the calculator here as well. Previously, I didn't pull it up, and I was just plugging numbers to my calculator, and you'd have to trust that I got the right answer, but hopefully now you'll actually see the right answer pop up on here. But without further ado, let's get started here. So the first question here, we're given some charges. So Q1 is 2, Q2 negative 2, and Q3 is also 2. And there's a 70-degree angle both here, and distance is 5. So this is really referring to the very first thing on the sheet, the very first thing we did, which is point charges. Let's first just examine what's happening between these charges on Q3. So Q1 and Q3, they are the same, and alike charges will repel. So what will happen is you get a sort of top right motion, and that can be broken down into like upwards and rightwards movement. However, these ones will attract because they're opposite forces. Opposite forces attract, so you just get a arrow pointing in this direction, which again can be decomposed into this upwards and or rightwards and downwards components. Now you can see it's a very symmetrical thing here, kind of configuration, and you can really reason that since these are again the same exact charge, just opposites of each other, the y component, right? If you're getting pushed a certain amount this way and the same amount this way, the y components will just cancel. And the x components will be the same, right? So these will completely cancel each other out. And these are both the same thing. So we just have to solve for the x influence of one point, and then we can multiply by 2 to get our final answer. So let's apply this formula here. So we'll start, represents k, which I'm not going to worry about units, I'm just going to put a 9. Then the two charges, again, we know direction, so we don't have to worry about units, 2 by 2. We'll divide by r squared, so that'll be that 5 centimeters squared. Again, like I said before, this is calculating for influence of one point charge, and we have 2 of the same. So we'll multiply by 2. And the last thing to consider is that we want the x component, right? Whereas this formula calculates the total component, right? The diagonal component. Now, we're given this angle here. This is 70 degrees, or theta. This here represents the y component, and this is the x. Since cosine of 70 is equal to like the adjacent side over the hypotenuse, what we're essentially getting is the component of the x force over the entire force. So we multiply by cosine 70 to turn this entire force into just this x force. We'll get 985, which effectively is this. So number 2 here, we're given electrons with initial velocity, a delta v between these plates of 5 and a distance of 2. So we're given a mass here, and generally when you're given a mass, it's one of two things. It's either a kinematics problem or a conservation of energy problem, just because those are the formulas that require them. Here we are worried about like distance, so we should be concerned. The only formula that deals with that is just the kinematics, so we should expect to see a kinematic somewhere here. But the issue is, to work on kinematics, we need a acceleration, right? And I mean, if we had a force, right, that's where the mass comes into play. So if we had a force, we could say that's equal to mass times acceleration. But where can we get this force? Well, we know that force is also equal to charge times electric field. Again, we do not have this electric field. However, I don't know if this is on the formula sheet. I don't think so. The electric field is just a ratio between the amount of charge between two things, the difference in potential, and the distance between them, right? It's just going to have that ratio, right? The total potential divided by that distance is that field. So we can actually redefine this as Q, V, and then I'll say S for the separation. So that's going to be our force. And if we're ever going to use a kinematic, which requires it, we can say something like Q, V, S over M is our acceleration A. Perfect. So now we want to solve for maximum distance. Well, let's think about this. X initial, 0, plus initial velocity, which we're given, so v naught 0, say times t, plus acceleration, which you solve for up there, times t squared over 2. I don't know why I put this in parentheses, but you get the point. So we have we have initial velocity, we don't have t. We can't really solve for t here because we have two unknowns. Generally with kinematics, what you do is you look into derive that equation and see what velocity can get you instead. So velocity at any time is equal to the initial velocity plus time times the acceleration. Now, the velocity at the time we're solving for is going to be when it's going to be 0 because of the fact that the electron's moving in this direction, and at a certain point it will come to a halt, and then it'll come back, right? And so the maximum distance happens when it comes to a stop or when its velocity is 0. So what we'll do is, we know this V naught, this is 8.4. I wonder if I have to use proper units. I'm going to try it without it, and we'll see what happens. 8.4, and then this thing. Let's calculate the acceleration real quick. So like I said, that's going to be Q, which is electron, which I think is 1.6. It's on the sheet here. 1.6, yeah. Times V, which is 5, times separation. Or no, sorry, electric field is not Vs, it's V over S. Oh, man. So we'd have something like this. My bad. My bad. So times 5, well, instead divide by 2, and then divided by the mass as well, which is the 9.1 here. So we'll say bad units, but that's the acceleration. So then we'll take 8.4 and we'll divide by this. This might screw up because I have to square this, so the units might have been the play here. But we'll do this, and obviously we know the acceleration is like negative, but we'll say that that is our t. That's the time. It's probably somewhere much smaller. It's not going to be 19 seconds, but again, we didn't worry about the exact scaling. So okay, 19.11. That's our t. So we'll just plug it into this equation now. So we have 8.4 as the initial velocity multiplied by this. Yeah, it seems very risky what I'm doing here, but again, you know, whatever. Remember that this acceleration is going the opposite way, so we want to put a negative sign here. Times this times the time squared, and then divide by 2. If this works, I'm going to be shocked. 80.26, which, yeah, does give us the correct answer there. I probably would recommend actually like converting the units so you do kind of verify that everything is correct. You're in the same magnitude, but you know, just using the numbers, we get the 8, so presumably it is correct. Okay, this question honestly is I think one of the few questions which like I don't completely understand straight up. So the idea is that you want to find surface charge densities, and you can do that just by finding flux. So these are where's the formula? These are infinite. Where's the formula? Where is it? Am I blind? Hello? Oh, here. Electric field is equal to density over 2 E equals density over 2 epsilon naught. The idea is that we're given the electric field, we can solve for the surface charge density. So just doing this on its own, right? It's much easier to approach this problem in like a terms of flux, which is going to be like the net electric field here, right? For instance, here with this one here, we have 1 unit of like the electric field coming in and 3 coming out. So we can say like the net field here is going to be 2. Similar here, there's 4 coming in. So we actually say that's -4 because something coming in is going to be like absorbed, that's negative. And then here, 1 coming out, 2 coming in, it's going to be -2. Now, we can add these up. You know, obviously we'll get a -4. And if we multiply this -4 by 2 and then by epsilon 0, which I think is 8.85, we will get this -70.8. And you don't have to do actually like all these things. You can say like, okay, I can treat 2, 3, and 4 as a continuous surface and just see that there's 3 coming in this side, 1 coming in this side, and so that's a total of -4. You don't have to technically add them up. I just think it makes more sense. You can see the correct answer here. It's number 1, and this is actually this answer divided by 2. My best guess here is that like if you try to reconstitute this field here, we can see that we're effectively like saying like this has an influence of 2 in this direction, and this has an influence of 4 in this direction. So that's total of 6, and it's supposed to be 3. So I think maybe it's just the truth that all of these values have to be half. I don't exactly know. It doesn't align with the formula super duper well, and it's not very intuitive for me either. Yeah, not 100% sure there. But now you know, so if there's ever a similar problem like this, and you get something like this, just know that you may have to divide your net values here by 2. Okay, so electric potential is given by this formula, and we have an area. What is the y component of the electric field? So if we look on our formula sheet, we can see that, I think this is the one we want, yeah. Sorry, that's not even area, that's just like a scalar. We can see that electric field in a certain direction is just equal to the negative partial derivative in that direction. So we want the y component of the electric field. Okay, that's just going to be equal to negative dv, like dy. So let's derive this with respect to y. So there's one y here. It'll get crossed out, and we'll keep its multipliers, which are a and this x squared, and this is a constant term. We get rid of it as well. It's just going to be ax squared. And we want it at this place, so x squared is going to be 1 times a, which is 2. Oh, and then obviously this negative gets put in here as well, so we just get -2. This is another one where we're given a mass. Now you can use kinematic equations on here, and that's actually how I solved it at first. But you don't have to, and it's a little bit easier because of the fact that you're actually like given a way to convert from voltages to positions. You can use the easier conservation of energy route and then just convert with the graph. So let's see what's happening. So we have a particle that's moving in a potential, and it starts with a velocity, and yeah, that's that. And it starts right here. So conservation of energy, what it says is that the kinetic energy at the starting point plus the potential energy at the starting point is equal to the kinetic energy of the endpoint plus the kinetic energy, the potential energy at the endpoint. Kinetic energy initial, kinetic energy is equal to 1/2 mv squared, which we can see that at this point we have m, we have v, we can calculate this. This is equal to, so U is equal to Q times V, and we're actually given V for this x equals 0, so we have V and we have Q, so we can calculate this. And from there, we just need K final. So what are we given? We can see here that the electric field, again, it's going to be equal to negative derivative of this V. It's initially going in one direction, It's good. It's initially positive technically, and then it goes negative. So what we can see is that it will actually this positive particle will follow in one direction of the field, and then it will head backwards because the electric field has now changed direction. So here, again, we're just assuming that at this point the velocity is 0, right? And since it's 1/2 mv squared, we know this is 0. And so this is what we're solving for here. So let's plug that in. Let's find the left-hand side first. So kinetic energy, we have mass 0.5 times velocity, so 2 squared, divided by 2. It's 1. Okay. And the potential energy is also just 1 times the charge, so 2, 3. And we know this is 0, so we know this final thing has to be 3 as well. Now the mass of the particle does not change. Or sorry, the charge of the particle does not change. So we can divide by 2 to just isolate this v. This v is 1.5. So if we look at when v is 1.5 here, it's at 2.5x. So that's our answer. So we didn't actually have to use the kinematic equations because this graph gave us everything we need to know relating v to x. Okay, this is a very straightforward capacitor problem. I like to redraw these so they're a little bit more straightforward. So we come out of the battery, we hit capacitor 1, which is 8. Then we split into capacitor 2 and 3. So we'll say 1 and 3. And then these two merge together, like so. And we go back into our battery. So we're left with something like this. Capacitors, they add like this, right? So here we get 8, 4, and then here in parallel they do this weird thing where it's 1 over each of the components is equal to the total thing. So this ends up with like a 2.7. Now we know the total voltage is 12 volts. 12 volts. And if we look at a formula sheet, the capacitance times the voltage is equal to our Q, our charge. So we can multiply this by the 12 volts to get a total charge of 32 coulombs. When this is split up, the voltage is split up, right? So both of these still have the same charge, but the voltage is split. So we can divide this by 8 to get the 4 volts that went here, and there's 8 volts that have gone here. Is that correct? Does that check out? I think so. All right, and then what is the voltage across capacitor C3? That is this one here. Dunk, dunk, dunk. Because now what happens is when they're split in series, the charge actually changes, but the voltages are the same. So these both maintain 8 volts, and the actual this would only have 8 coulombs, and this would have 24. But the important thing to note is that the voltage here stays the same, so we just end up answer 1. Equivalent resistance of a combination. Again, we'll do a similar thing. We'll start here. We encounter one resistor, which 300. Then we split off into 1, 2, 3 branches. So we have 1 300 up here, 1 300 here, and 1 300 here. And then all 3 of these branches meet back up and exit the system. So we're left with something like this. Now resistors add with the opposite rule of the capacitors. So here they add inversely like this. So let's go 1 over, and then I'll just go 3 over 300 because that otherwise it's 1 over 300 plus 1 over 300 plus 1 over 300, just 3 over 300. It's a little faster. We get 100. So then we have 300 and then 100. And so these, when they're in parallel like this, again, they do the opposite of what the capacitors do. They just add up straight. So we're just left with 1 resistor of 400 ohms. Perfect. Again, a very, very similar problem. Battery goes this way. We split into 1, 2, 3 paths here. So that's 2, 3, and 4. 2 is 100, 3 is 200, and 4 is 200. These 3 all meet up. And then they pass through R1, which is 100, and get back to the start. So 100, and they're back. Okay, again, we will combine these. So 1 over, I'll go 2 over 200 plus 1 over 100 here. Again, this is just saving me from writing 1 over 200, 1 over 200. And we get 50. So this is a 50, and this is a 100. Add those two together, 150. The total across this is 12 volts. So unlike the capacitors, this uses V equals IR, where I is the current. Now, if we go 2 divided by 150, this will give us the current over this. We'll go 0.13. And here, the current actually stays the same, right? Because they're on the same wire. So both of these will have current 0.13. This 2 volts will actually get split up into like 1.3 here, right? Just multiplying these two. And then like this will be like 0.67. We want R2 here, which is the singular 100 circuit. Remember, this is where the current will split. But remember that when they split, like when everything splits like this, the voltage stays the same. So this is 0.67. And we get 0.67. No, that's not right. What am I doing? So yeah, the current will split here. I don't even think I did write it down for this problem. Oh, I think I just did my initial calculations wrong. Oh, I wrote 2 instead of 12. Sorry. 12 divided by 150. 0.08. Again, this stays the same here, 0.08. This is distributed proportionally 8 volts and 4 volts, splitting up that 12 volts. So each of these, have 4 volts. When you divide that by 100, you get 0.04, which is equivalent to this answer here. My bad. It happens. Hope I don't make those mistakes on the exam. All right, what's the current in amps through resistor R1 long after the switch is closed? So this is an inductor. What happens is it resists changes in charge. So if the switch is closed, all of this portion of the circuit will jump from 0 amps going through it to like all of the amps from this EMF. And so this will kind of keep it at 0. So this part will not exist. Everything will just flow through here. However, after a long time, that effect's worn off, and this just acts like a regular wire. Now, the thing to note is that if you have the choice, if current has the choice to flow between the normal wire and a resistor, it's just going to choose the normal wire because it's easier. So effectively, all we end up with is R1 at the top, goes around to the normal wire, goes back to the battery, right? That's all our circuit is. And you can even like visualize it as like being R1 and then splitting into R2 and then like a resistor of resistance 0, right? If you add those up, you're going to end up with like 0 resistance here. Well, you'll get a dividing by 0 error because you're trying to make 0 resistance here. It just doesn't work. So everything goes through the wire instead. And, 3 volts, 10 resistance. It's 3 divided by 10. There you go. Negatively charged particle has a velocity which along magnetic field directions would produce that force. It's negative, which means the right-hand rule, take the inverse. And right-hand rule is simply point in the direction of V. This might be mirrored. I don't quite know what you're seeing. V, V. So point in the direction with V with the front of your fingers. And your thumb will point in the direction of F. Okay, this is actually too confusing for me to flip. So point in the direction of V. It's going to be flipped for you guys, sorry. And then your thumb will point in the direction of F. Now we want F to be pointed down and to the right because of the fact that for a negative particle, it's flipped. So that means your fingers, where do they curl? They curl towards me. That's out of the page. So again, if you right-hand rule, if you point your fingers in the top right and your thumb in the bottom left, if they were top left, that would constitute to a positive particle, which would be into the page. You take the opposite, which is out of the page. Magnitudes of currents, directions, the magnetic field, center of the square. Okay, again, right-hand rule. If these are coming out of the page. So stick your thumb towards yourself and see where your fingers curl. My fingers are curling in like this direction, right? And the same thing happens here, right? It's the same. So I like to, when I do these problems, I like to represent them with like diagonal lines because I think it's a little bit easier, but you can see this kind of bridges the gap within these circles. If you instead, this represents sticking your thumb inside the page, curling there will give you something like this. Oops, something like this. And again, creating those diagonal lines to bridge the gap will constitute something like this. So now all we care about are these 4 diagonal lines. We have boom, 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 boom. You can see that all of them are headed in this positive x direction, and the actual like y's cancel each other out, like these cancel each other out, these cancel each other out, so we just end up with positive x movement. Okay, a circular loop, uniform magnetic field, it's rotated. What's the amplitude of the EMF induced? So EMF induced is clearly a magnetic flux problem right here. So during a magnetic flux problem, this is how I kind of like to solve them. They have these formulas here. I don't really use it like that. What I basically say is there a change in area? The loop is a constant radius 10, so I just put A. If there was a change in area, I would put like dA, or the change, but since it's not changing, I just put A. Then I ask myself, oh, is the magnetic field changing? No, it's not, so we'll just put B. Again, if the magnetic field was changing instead of the area, you'd have A times dB, right? You'd put the derivative of the magnetic field instead. But here, there's something else. So these two are not changing. What could be changing? It's just the angle. And so again, you just kind of want to multiply all the stuff that's the same times the one thing that's different. So here, how do we get the rate at which the angle is changing? Well, we're given this. The loop rotates at 60 rotations a second. That is our frequency f. That is omega over 2 pi. So we can get omega by multiplying this by 2 pi. So say we multiply that by 2 pi. What does this give us? Well, this is rotations, and there's 2 pi radians in a rotation. So this will give us a certain amount of radians a second, which is what omega is. And that's the rate of change of the angle. That's our d theta, which we want here. So what we can do, again, the two things that are held constant, we just multiply them times the one thing that's changing. We'll throw that in. So we just get that, well, first we need the area, which is going to be like 10 squared times pi times 1 for our magnetic field, and then d theta, which is going to be the 60 times the 2 pi, which gives us 11.8, more or less. If we had just adjusted for this, that would have been right on with the magnitude, but again, we care about the 11.8. All right. Capacitor is connected to an inductor, and they're flip-flopping their energies. What's the inductance of the conductor when the current is this? Or the maximum current? So there's not much to go off of here, but really what you have to realize is you're given like an initial energy for the capacitor, and then that energy will just flip-flop back and forth. So let's start by finding that initial energy for the capacitor. UC, where are you? Inductor, capacitor. UE. Do we have Q or V? We're given Q. So UE equals Q squared over 2C. UE equals Q squared over 2C. You can calculate this. I'll go 30 squared by 2 divided by 1. It's somewhere along the lines of 450. 450 times 10 to the something. That's not 450, 450. So we need this same energy later into the oscillations, right? And the time at this point, we have the maximum current in the circuit being 2 amps. So that occurs when everything is in the conductor, or in the inductor rather. And this energy here, UB, so the max energy there, is equal to Li squared over 2. Li squared over 2. We have I, that's 2, and we have 2 squared times L over 2. So we have this, we'll multiply by 2, divided by 2 squared, and we'll get 225, and that is wrong. So I think this is some unit-related shenanigans. I could just be doing something wrong, though. It happens. Happens a lot. Let's see. I mean, here, you can see the solution here. Oh my god. Sorry, I plugged. This is bad, dude. If I do this on the exam, I'm cooked. I plugged in the capacitance for the charge and the charge for the capacitance. So there you go. We should end up with something like this for the energy, where it's this is the capacitance. The farads is the capacitance, which is on the bottom. So put it on the bottom. Jesus. Yeah, divide by 2, and you'll get the answer for L. All right, number 14. Oh, okay, this one's weird. You have to know how to do this one, but it's not super intuitive or anything like that. So we have an electric field, which is given by that. There's the cube, and we want to know the net electric flux. So the net electric flux is just how much is passing through. It's how much is coming out minus the amount coming in. Oh, God, what's happening? So I guess I'll redraw the cube here. Oops. All right, so let's look at this this friggin' thing here. We can break it down into components. 10I and this monstrosity for J. So if we think about it, there is no Z component in the electric field. It's only headed in like this direction or something. Maybe it looks different, maybe it looks like this, but it's just headed in that direction. So there's going to be nothing coming in this way and nothing coming out this way. So both of these are going to be 0. They don't constitute or contribute to the flux. Now, this X component, if we again we can break it down into like a Y component and an X component. This X part is only going to get affected by the X component, and the X component is always just equal to 10. So it's 10 coming in and 10 coming out. Net electric flux, it's stuff coming out minus stuff coming in, so those cancel each other out as well. So we really only care about this these top faces in the Y direction. So this top face and this bottom face. So in this bottom face, Y equals 0. So we have like a 5 times 6 electric field in that direction. Here we know the cube is of edge length 0.5, so we'd have 5, 6, 0.5 squared, 0.25, 6.25 is the total stuff there. And if we subtract these two, it would just be 5 times 0.25 for the difference there. Now, that's the difference in like the electric field. But also another thing you have to realize is that we want to calculate this based on the size of the cube. And so the larger the face is, the more this matters, right? The more greater the amount of flux is as it comes out of that top face. So we'll just straight up multiply by the area of this to scale this kind of unit flux up to the actual size of the cube. So what ends up happening is you get 5 times 0.25 times 0.5 squared, and that gives 0.312. And again, you're having more come out from that top face than you are having come in from the bottom face, so it's going to be positive. Polarizing. This should be free, as long as this has like a really confusing diagram where it looks like this diagram isn't related because it says like 0, but it like is, and you will get it wrong if you don't look at the diagram. Besides that, polarization should be free because it is literally just plugging into formulas. There's nothing they can really do to complicate this. So what fraction of the initial intensity? So we'll say, initial intensity is going to be just 1. So this is unpolarized. The first time unpolarized light goes into a polarizer, the intensity just gets halved. So this just becomes 1/2, right? We turn from 1, halve it, 1/2. Now, the light is now polarized at angle 0 degrees from the y-axis. So it's now polarized like that. Where are the formulas? Here. So at this point, it passes into the polarizer, which makes this 30-degree angle. So it's trying to now polarize to this, where this is 30 degrees. And so the difference in angle is that theta, right? That's the 30 degrees. And that's the fraction we multiply by. So we have that 1/2. So I'll say we have a 0.5. And we multiply that by cosine of that angle, 30 squared. There we go. That's how much is now being taken out in this direction. Now, delta 3 is 45. You can't just say like, oh, it's 15 degrees separate, because what this actually means is a 45-degree angle like this. Not like this, but like that. So you end up literally going like this direction. And it ends up being this 35 degrees here plus this 45 degrees here, which is the total difference in angle. So we'll take this, and now we multiply by cosine of 75 degrees. Again, that 30-degree angle there, plus that 45-degree angle. Square it, and we get this, 0.25, 0.025, whatever. All right. Light goes into a slab, index of refraction. What is the angle at which it leaves the slab? Snell's law here. This is plug and chug. There it is. What this means is we have an initial air or index of refraction, an initial entry angle, which anything you do with this law has to be like corresponding to the angle's normal, right? So they give you this angle is 30 degrees. We don't care about that. What we really care about is that this angle is 60 degrees. That's the angle we actually operate with in the formula. It's always the angle normal to the surface you're going into, not the angle parallel. So we'll say N1, and we'll say N1 is the index of refraction of air, which is just 1. And so we'll say, well, that's supposed to be sine of 60 degrees is equal to N2, which we know is 1.2, times sine of, the angle normal to where you come out. Or sorry, this is, I'll call this angle internal. We're calculating for this angle here, angle internal, I'll call that. We're not quite there yet. So if we calculate that, it's really just going to be sine of 60 divided by 1.2, which gives us this here. And then we can inverse sine that to get our angle in here, which is 46 degrees. Now, this angle is the same as this angle. It's true. But remember that for this law, we always care about the angle adjacent to the normal, right? So we want this angle in here instead. I know it's getting messy. So we don't care about this angle, which is what we just calculated for, but we want this angle in here. So when we end up doing the calculation, we'll go N2, and then we actually, again, care about that normal angle, so it's going to be 90 degrees minus that 46-degree angle, equals N1, which we know is 1, so 1.2, and sine of that end angle theta. So we have 1.2 times sine of 90 minus 46, inverse sine it, and we get 56 degrees. All right. I personally think that the lenses are a fairly easy unit. only thing you have to know is the sign conventions, which you don't really have to memorize. You just have to kind of think about. Like if I have a mirror, I expect the if I have an object here and it's getting reflected, I expect the image to be on this side. So that is a positive. So yeah, okay. And the only formula we need then is this, right? Or this. They're equivalent because R is just or F is just like R over 2. So we can use this formula here, which is, it's written here, but 2 over R is equal to 1 over P, the object distance, plus 1 over I, the image distance. And so, yeah, we'll say that a positive image distance is when something is on the same side of this, because that's what we expect. Right? I think you should look over all the things, especially for lenses, is where it gets a little more complicated. But again, we'll just continue with this formula. 2 over R is going to be that 50 minus that object distance, which is 1 over 10. And so we'll get a 1 over, so we'll get an I of negative 16.7. Is that correct? I feel like I have screwed up the signage somehow. No, I don't think I have actually. So this is our I. Was I wrong about this? Is this not supposed to be positive? Whatever. We get our I. If we then look at the formula for magnification, it's negative I over P. So negative, or I'll say negative 1 times I, which we know is negative 16.7. Well, it's not actually. And then P is that. We get that 1.7. So now there's lenses again. So we have 2 converging lenses, which I say here and here. For converging lenses, again, the focal point, you do have to know, they give you the length, but you have to know the if it's positive or negative. So for a converging lens, it's positive. So this is a plus 10 focal length, and this is a plus 10 focal length. And this is just applying the formula twice. This formula up here, because that's really just all you have to do for lenses. So this is 20 centimeter gap here. That is a tiny, tiny 20, and this is a 25 centimeter gap here. We want to know the final distance from an image shoot. So we'll start with, so 1 over F is equal to 1 over P1 plus 1 over I1. So 1 over F, that's going to be the 10 there. And then this is standing to the left of this mirror, which we say it's positive. So we will subtract 1 over 20. That's where it's standing relative to the first one. We're just doing the calculation for the first mirror right now. 1 over that, divided by that, gives 20. So we know that since this is positive, we know that this is to the right side of this mirror. Because what this is actually doing, this lens, is it takes these light rays and it converges them together. So we expect the image to be on this side, so we say that this side is positive. So it's 20 centimeters this way, or 5 centimeters from this lens 2. So when we end up doing the calculations for lens 2, 1 over P2, P2 is actually that 5 centimeters because that first image is 5 centimeters away from that second lens. 1 over I2. I2 is what we want to solve for. So 1 over F, it's just 10 again, minus 1 over 5. 1 over that. We can see that we actually get negative 10, which unlike we did here for a positive 10, negative actually implies that it's to the left of that lens, right? So if that lens converges stuff to give a positive outcome, that's actually means it's to the left. Yeah, negative if the image is to the left of the lens. But again, since we use the right sign conventions, we didn't even have to know that. We just use what the formula output. Okay, double slit interference. This I think is also fairly easy. Just know what the variables in the formula are. So like this double slit, like what is D? What is A? They're not terribly complicated. This is what it is. So double slit. We have a 600 nanometer wavelength where it's fourth order maximum, where that means this, where m is 4, occurs at an angle of 90 degrees. So this is 90 degrees, which means sine of theta is 1. So what we get is d sine theta, sine, sorry, is equal to m wavelength. So this is 4, it's the fourth order maximum. This is 600. And this is just 1, because sine of 90 degrees is 1. So that implies that the distance between the two slits currently is 2400, I don't know, nanometers. Nanometers, yeah. And what we want to do is we want to change this distance in the slit separation, because that is what the D stands for. It's that distance between the two slits, such that all of the visible light is gone in the fourth order maximum. So if we kind of like look at what's happening now, a sine of 90 degrees implies that that light's like being eliminated, right? It's not going to hit the backing. So if we say that like sine of theta, sine of theta, which sine of 90 degrees, 90 degrees is 1, and you can kind of think that like anything that's below that is just going to hit that like backing board and it'll be shown. But if you get greater than 90 degrees, if you somehow create a ratio of m wavelength over d that is greater than 1, then it's not able to be solved in the sine, and therefore it just doesn't work. It doesn't. You can't observe that wavelength. So we essentially want all of these wavelengths to be over 1 here. So currently, that D is 2400, right? If we take the fourth order maximum, 4 times 600, and then divide by 2400, the D we solve for, we can see that that is 1. That is like the largest, or the wavelength at which it's exactly eliminated. Anything that is smaller than that, say I did 4 times 400, 1600 over D, that would be less than 1, and therefore it wouldn't be eliminated. But again, we want to eliminate everything. And so what we actually have to do is, we just saw that going to a smaller wavelength decreased the sine. So that means that if we like solve for a new D for 700, that means that 400 could still get passed. However, if we solve for what D eliminates this 400, everything larger than the 400 would just create a greater sine and just be impossible to cast as well. So again, we'll do the same thing. We'll assume that here sine of theta, just like we did at the start, is going to be 1. And we have m, which is 4, and then our wavelength, which we're now defining to be that smallest wavelength in that visible spectrum, that 400. And so we just get d equals 1600 here. And the distance there is 800. And finally, we have a single slit diffraction pattern. This is the width of that single slit. So the distance between the first and fifth minima, this only shows us minima. A sine theta equals m lambda. A sine theta equals m lambda is 5 millimeters with the screen 50 centimeters away when a wavelength of 600 nanometers is used. Sorry, this should not be theta. This should be wavelength. So when we plug this stuff in, we don't know A. I'll get back to sine of theta. M is the distance between the first and fifth. So effectively, that's just like, that's 4 minima. We can do like that. So we can like take the distance of like the fifth and then subtract the distance for the first. And this will just end up being 4. But we want, it's constant. So we have first minima and then fifth minima all the way over here. We just want that distance, which is the same as just taking 4 minima over. And so sine of theta, what else are we given? Well, we have the actual distance. So say this is the slit and this is the board we're like projecting on. We have the distance here as 5 millimeters. And then we have 50 centimeters as how far away the screen is. And we have the wavelength. Obviously, this is going to be 600. So if we take sine of theta, well, we can determine theta by taking an inverse tangent, right? Opposite over adjacent is going to give us that inverse tangent. So I'll go like 5 e negative 3 divided by 50 e negative 2. So that's our angle theta. And then if we sine our theta, we will get this. So the tangent or the sine is just equal to 0.01. Kind of an indicator that we're on the right track there with how nice that number is. So we can solve for a now. It's going to be 4 times that 600 divided by 0.01. And in fact, I'm going to adjust this so that it's 4 times 600. Since I've been diligent with the units, I'll go all the way. Nanometers is 10 to the negative 9th, 0.01. And we got that. Just because with angles, you want to make sure you're using the right units. And then we want the angle of the third diffraction minimum. So we have our A, 2.4 e negative 4. And again, we're just going to use the same exact formula, right? We want the angle. So we'll just start with sine theta is equal to m wavelength over A. M is 3. Wavelength is ever still 600. We can put in the units. And we divide by A. It's here. So we get this. Then we'll take the inverse sine because we want the angle. And we get 0.43. So that's the solution. That's everything. If you want to talk, leave something in the comments. Hopefully that helped. Well, maybe with everything except for this problem, because this problem, look, this is the day before the exam. I can get a question wrong. That's the one I'm going to be getting wrong. Well, I guess apart from every other question I made a dumb mistake on, but that's besides the point. It's the glory of the multiple choice exam. All right, good luck. I'll be making another one of these for the 2024 exam, but if this is the only one you watch, good luck with your studies.